Welcome to the next lesson in our Cosmic Adventure lecture series. My name is Dr. Valerie Rapson, Assistant Professor of Physics and Astronomy at SUNY Oneonta and past Director of the Dudley Observatory. Today we are going to talk about two of the next generation telescopes, the Rubin Observatory and the Roman Space Telescope. These are two amazing facilities that will be coming online in just the next few years, and they will produce an amazing amount of data in all areas of astronomy. Things like exoplanet science, supernova studies, the search for dark matter and dark energy. These telescopes are going to be able to contribute to all of these areas of astronomy. Today I'm going to introduce you to these new observatories. We'll start by giving you a little background about their namesakes, Dr. Nancy Grace Roman and Dr. Vera C. Rubin. And then we'll talk specifically about the facilities. What do the telescopes look like? What are the cameras and other instruments on board? And what is the science that each observatory hopes to focus on? Let's begin with a brief summary of these two observatories. Astronomers are always looking forward to the next big telescope. What can they build that will allow them to peer deeper and deeper into the universe? These two telescopes are a great example of this future vision. On the left-hand side, we have the Nancy Grace Roman Space Telescope. It's an optical and infrared observatory that's actually the same size as the Hubble Space Telescope, but it's designed in a different way so that we can actually take larger pictures of the night sky. So this will give us images of equal quality to the Hubble Space Telescope, but we'll be able to see more of the night sky at once, allowing us to take even better pictures than the Hubble Space Telescope did. On the right-hand side, you see a cartoon of the Vera C. Rubin Observatory. This is a ground-based observatory and telescope located in Chile in South America. And it is an optical telescope that will constantly scan the southern sky to give us 10 years worth of data. We'll be able to study how the night sky changes in that time and also look for evidence of dark matter, dark energy, and really get a sense of the structure of our universe from this surveyed telescope. We'll get into the specific details of each observatory in a moment, but before we continue, I just want to mention how amazing it is that these two observatories are named after female astronomers. It has taken quite some time, and honestly too long in my opinion, for our women astronomers to be recognized for the fantastic work that they have done over the years. And I'm just really excited that we have finally named two large telescopes after two fantastic female astronomers. We're going to begin by talking about the Roman Space Telescope. I'll introduce you to Nancy Grace Roman, and then we'll talk about the telescope a little bit more. And then we'll jump over to the Rubin Observatory, talk about Vera Rubin, and the amazing things that we hope to do with that observatory as well. Nancy Grace Roman was an amazing astronomer and a huge advocate for getting women involved in the sciences. She got her PhD from the University of Chicago in 1949 and was actually the first woman to hold an executive position at NASA and was the first formal NASA Chief of Astronomy from 1960 to 1979. You can see a picture of her down in the left-hand corner here. This is Roman at NASA's Goddard Space Flight Center around 1972. And during her time at NASA, she really pioneered this idea of building space-based telescopes. She also really tried to get more young women involved in the sciences. She tried to recruit more women to NASA and also did a lot of work with children just to get them excited about science and show them that they too can become an astronomer. Because of her pioneering work at NASA and all of her work with women in STEM, LEGO actually made a Women of NASA kit and included Nancy Grace Roman as one of the little Lego figures. You can see a little Lego figurine of her here on the right-hand side, standing next to the Hubble Space Telescope. This is like a dream goal of mine, right? To be special enough that LEGO recognizes you and actually makes a little Lego figurine honoring you and all of the work that you've done over the years. So maybe someday I'll have a little Lego set for me too. Now, because of her work pioneering this idea of space telescopes, a lot of people affectionately call Roman the mother of Hubble, meaning the mother of the Hubble Space Telescope. She really laid the foundation for this large space telescope program. Her and Lyman Spitzer really had this vision of doing science from space and being able to study the night sky without having to wait for it to be nighttime or worry about observing through the Earth's atmosphere. There were a lot of challenges that had to be overcome to build and launch a space telescope, but the amount of science that could be done above our observatory is just so much greater and well worth all of that effort to design these space telescopes. So during her time at NASA, she oversaw the development of the Orbiting Solar Observatory Program and the Orbiting Astronomical Observatory Program. These were sets of telescopes and observatories that ultimately launched into space. And sometimes they weren't quite successful at first, but later on in the program, these observatories provided some amazing scientific data and really showed that space-based observatories were something that we could do, that we could build and launch and successfully use in the future. She also oversaw the X-ray satellite program in the 1970s and ultimately, again, laid the foundation for the design and the launch of the Hubble Space Telescope and really all of NASA's great observatories. So let's transition to talking about the Roman Space Telescope, how it got started, and you'll start to see why this observatory specifically was named after Nancy Grace Roman. Every 10 years, NASA scientists get together and they create what's called the Decadal Survey. Basically, they decide what important science they want to get done over the next 10 years and what facilities or equipment they need to build or start to plan for to be able to do that science. In 2010, two big things kind of came out of the Decadal Survey. Scientists decided that they wanted to search for exoplanets, so look for planets around other stars and get a general census of how many there are, where they exist, and things like that. And they also wanted to study the edges of our universe to look for evidence of dark matter, dark energy, and understand more how both of these mysterious materials have influenced the evolution of our universe over time. The title of the survey ended up being New Worlds, New Horizons, right? Studying exoplanets as well as looking to the edges of our universe and learning more about how it evolved and changed. And this decadal survey really pushed for a moderately sized telescope that could do both of these things, that could help us search for exoplanets, but also study the edges of our universe. So in 2011, plans began for a 1.3 meter telescope that was originally called WFIRST, stands for Wide Field Infrared Survey Telescope. And the idea for this observatory came out of the Decadal Survey, but it was also spawned by this project called the Joint Dark Energy Mission. This was a joint mission between NASA and the Department of Energy, where they had plans to build a 1.3 meter telescope that would really focus on looking for evidence of dark energy and trying to study how dark energy has caused the expansion of our universe and whether or not that will continue indefinitely into the future. Now, this is definitely not the largest space telescope ever planned. But it definitely was going to provide a large field of view. Instead of building a big telescope that could look at a small patch of sky, this telescope was going to survey the sky, looking at big patches of the sky at once, but with really good detail, creating a survey of objects in our night sky. So that was originally the plan, build this mirror and this new telescope and launch it by the mid-2020s. But then NASA actually got a gift. In 2012, the National Reconnaissance Office gifted NASA two 2.4-meter mirrors, which happen to be the same size as Hubble. The National Reconnaissance Office is the organization within the US government that actually builds spy satellites. So these two mirrors were originally going to go on satellites and stare back down at the Earth. But these projects were canceled, the mirrors weren't needed anymore. So they were gifted to NASA, and they decided to use these mirrors, point them in the opposite direction, and put them in a telescope to study the nighttime sky. Now, what was really great about these mirrors is they were the same size as Hubble, which means that we can get the same high quality images as the Hubble Space Telescope. But the mirrors had a shorter focal length, meaning that that was going to give us that wide field of view that our project had hoped for, that we had planned for designing WFIRST. Just to kind of show you what we mean by field of view and focal length here, you can take a look at the cartoon on the right-hand side. Focal length is basically the distance from the mirror to the position where all of the light will come to a focus and you are able to see a nice crisp image. The three pictures here show three different focal length telescopes. So you might imagine down here at the bottom that there's a mirror that light is bouncing off of. That mirror is curved, so that's going to cause the light to travel forward and eventually collect together at a focus, at the point where the two lines from opposite sides of the mirror converge together. If you have a short focal length, that means that your light comes to a focus at a shorter distance away from the mirror. And if we were to continue to draw those lines outwards, you see that if we were to take a look at the amount of sky that we are collecting light from, you can see that that angle is really large. So when you have a short focal length mirror, your angle of view or your field of view can be really big. You can see in this example, 5 flowers wide. As you make the focal length longer and longer, you are narrowing the amount of sky that you are able to see. So here in this example, kind of a mid-range focal length, if I trace it out, my field of view is only 3 flowers wide. And at the longest focal length example here, I can only see 2 flowers wide. With many large telescopes, this is not a problem. They often have larger focal lengths, and we're looking at a small portion of the sky in really high detail. But with these mirrors and this observatory, we were going to basically get the first example here, where we were going to get a high resolution, highly detailed image over a really large field of view. What this ultimately means is that WFIRST can image a large portion of sky with the same resolution as Hubble. So it'll take less time to gather even more equal quality data to the Hubble Space Telescope. So overall, this was fantastic. They adjusted their plans to utilize one of these mirrors in the telescope, and we were going to have this wide field survey observatory like we originally planned. So in May 2020, NASA decided to rename WFIRST to the Roman Space Telescope. And here are some of the basic stats of the telescope. We saw that it's going to be a 2.4-meter telescope that observes in both the optical and primarily the near infrared. It's going to have a 0.28 square degree field of view. That is a little bit larger than the full moon in the sky. So if you think about how much of the sky the full moon takes up, this is just slightly bigger than that. The cameras on board, and we'll talk about these in more detail in a moment, they are a total of 300 megapixels, along with a spectrometer device that will be able to do spectroscopy, break up the light into the rainbow of colors, and study the composition of objects in more detail. And the telescope will also have a coronagraph system. This is a device that can block out light from a star and allow us to directly observe exoplanets orbiting around those stars. Now, the way that this observatory is going to work once it is launched is that scientists are going to have two different opportunities to do observations. Initially, this will be a survey telescope, meaning that it's going to scan large portions of the night sky and give us big pictures of a large patch that astronomers can study for a variety of different reasons. Scientists will draft what they call white papers, which basically explain the portions of the sky that they want the observatory to look at first and provide these large surveys for. And then after these large surveys are complete, the telescope can be used for specific pointings. So a scientist could write in and say, I really want to look at this star or galaxy or nebula. Can you point the telescope at it for X amount of time and let me look at it because this is the science that I want to do. So this observatory will be a combination of a survey telescope as well as a specifically targeted observatory. Let's take a look at the two pieces of equipment that are on board the Roman Space Telescope. That would be the wide field instrument, which is the main camera on board, as well as that coronagraphic instrument. There are two really great videos that briefly explain how each of these instruments work. So I'm going to start by playing the video for the wide field instrument, and then we'll briefly talk about some of the data that comes back, and then I will show you the video for how the coronagraph works.
The Wide Field Instrument is the heart of the Nancy Grace Roman Space Telescope. It is what allows the Roman Space Telescope to take pictures with the same detail as Hubble, but covering an area 100 times larger. Despite this incredible power, the basic design is the same as telescopes around the world. Light enters through Roman's 2.4-meter aperture and is reflected and focused by the curved main mirror, which is also the largest mirror in the telescope. This light is reflected and focused once more by the secondary mirror. More elements tighten the beam and strip it of stray light rays before it passes through the filter wheel. This wheel has a variety of filters that allow different wavelengths of light to pass through. It spins from one to another depending on what the researcher is looking for. Finally, the focused and filtered light reaches the focal plane, where it creates an image on the detectors. These detectors use the photoelectric effect to convert photons into an electrical signal that is then decoded into an image. In Roman's case, there are 18 detectors, allowing it to create 300 million pixel images of large patches of the sky. The large number of detectors and pixels gives Roman its wide field of view. The size of the mirror and the precision of its optics gives Roman its fine imaging. This combination of image size and detail has never been possible on a space-based telescope before, and will make the Nancy Grace Roman Space Telescope an indispensable tool in the future.
So that gives you a sense of how the wide field instrument or the main camera on board the telescope works. By changing that filter wheel, astronomers can choose which filters they want to look through for their observations. And because the CCD is so large and they're gathering such a wide field image, the amount of data that's going to come back from the Roman Space Telescope is just tremendous. On average, the camera will send back over 1.3 terabytes of data per day. That's so much more than any other telescope has ever sent back. So that kind of leads into another challenge that astronomers are going to have to think about is how do we handle that much data and how do we allow people access to that much data all at once? We can also take a look at the coronagraph on the Roman Space Telescope and see how that works and how it will allow us to detect planets orbiting other stars. So let's watch this short video to see how this piece of equipment works.
A coronagraph is a way to see distant planets hidden by the glare of the star they orbit. The coronagraph reduces the light coming directly from the star to separate it from the light reflected by the planet. The Nancy Grace Roman Space Telescope's coronagraph doesn't block the star's light with an opaque disk, as a simple coronagraph might. Instead, it uses a combination of disks with complex patterns and light-blocking stops to create destructive interference with the star's light. effectively making it disappear while allowing the light from planets to pass through. A complicating factor is that the light picks up small distortions as it reflects off the telescope's series of mirrors, and these distortions can reduce the effectiveness of the destructive interference. Collecting more light increases the image signal, but the planets are still hidden under blobs of leftover, distorted starlight. To remove these blobs, the coronagraph has special deformable mirrors that can change shape by using hundreds of tiny pistons. This corrects distortions in the light beam. As the mirrors deform, the blobs of light slowly begin to disappear, revealing brighter planets. Further adjustment brings fainter planets into view. Advanced software processes this data, further improving the contrast and clarity of the image. This processing makes objects more than 1 billion times fainter than the star visible. As a result, the Roman Space Telescope will provide the first look at individual planets in star systems that might be similar to our own.
So the coronagraph on board this space telescope is really state of the art. And as you saw with that video, the coronagraph is a little bit different than the types of equipment that we have here on Earth. Many of the coronagraphs that we use on ground-based telescopes literally just have a blocking mechanism. You can imagine on a sunny day going outside, looking up in the sky and holding your hand up and just blocking the sunlight. That's how most of the coronagraphs work. But this one is much fancier than the others. It uses that special technique to basically cancel out the starlight or the light from the central star so that we can see the exoplanets around the star. It's also the first time we have ever used adaptive optics on a space telescope before. So I really hope that this works well. There's no reason that it shouldn't, but I'm just excited to see how it works. And if it does work well, this could be something that we see fairly often on other future space observatories. Let's do a quick comparison between the Roman Observatory and two other telescopes that you've probably heard of. The Hubble Space Telescope, which we've talked about a little bit today, but also the James Webb Space Telescope that you probably know is hopefully going to launch in the near future. Here we're comparing three things for each observatory. We have the mirror size on the left, the field of view, or how much of the sky each observatory is able to see in one photograph, and then the wavelengths of light that are studied by each telescope. We saw already that the Hubble and the Roman Space Telescope both have equal-sized mirrors, which means that the precision and the resolution of the images is going to be about the same. The Webb Observatory has a much larger mirror, and that means that those images are going to have higher resolution. It also means that the field of view is going to be a bit smaller, at least compared to the Roman Observatory. If we switch over and look at the field of view here, you can see that this box represents the size of the Hubble Space Telescope's field of view. Here is the Webb Observatory field of view, and then this whole big thing up here, this is the Roman Observatory field of view. All of it is overlaid on top of a real photograph of M31, the Andromeda Galaxy here. So you can see that in one picture, we can see much more of the night sky, and that picture is of equal quality of the Hubble Space Telescope. And the Webb Observatory is only going to allow us to see a smaller portion of the sky at once, but the resolution is going to be greater. So these three observatories are going to work in tandem. I'm not trying to say that one observatory is better or worse than the other. They all have different strengths, and we're going to be able to use information gained by all three of these telescopes, maybe even at the same time, to be able to observe a variety of different things in our night sky. The bottom here also compares the wavelength that is studied by each telescope. Hubble has capabilities to look at the UV, visible, and a little bit of infrared light. Roman does some optical as well as near infrared. And then Webb is really an infrared-only space telescope. So not only are their field of views a bit different, but the type of light that they study is different as well. And this will allow us to study different things about objects. An object might emit light at visible and infrared wavelengths, but for different reasons. And by being able to look at a single object at different wavelengths of light, we can start to collectively understand all of the science that is happening with that object. So each one of these observatories is going to be really helpful to astronomers, and it's great that we are going to have all three operating and sending us information about the night sky. Let's transition now to talking about some of the science that we hope will be done with the Roman Space Telescope. There are a variety of different fields of astronomy that this telescope will contribute to, but I'm just going to highlight some of the main mission objectives in the next couple of slides. One of the main things that we hope the Roman Space Telescope will do will teach us more about the universe in general. Basically, what is the overall large-scale structure of the universe? What are the origins of dark matter and dark energy? And what might ultimately happen to our universe in the distant future? To answer some of these questions, we need to really get a nice deep view of the night sky. We might look for things like gravitational lensing caused by dark matter. In the picture on the bottom left here, you see a couple of galaxies in a cluster here, and some blue arcs around the outside, which is actually light from galaxies behind the yellow ones that bends around the foreground galaxies and gets magnified and distorted by the presence of dark matter within that yellow galaxy cluster. We'll talk more about gravitational lensing and dark matter when we talk about the Rubin Observatory, but I just wanted to mention it here because it is part of the Roman Observatory objectives. So we can learn a little bit more about dark matter this way. We can also learn more about the history and evolution of our universe by spotting supernova. By looking at distant galaxies, like this one shown here, and spotting bright dots that were never there before, like this supernova explosion from 2007, we can measure the distances to these galaxies using properties of supernova, and ultimately understand how large our universe is, what was the frequency of supernova, and a bit more about the evolution of the universe and how dark matter and dark energy has caused it to change in time. So supernova can help us determine that. And finally, we can also study galaxy structure. Basically, how are the galaxies distributed in the universe? Are there lots of spiral galaxies and elliptical galaxies in one location? Are they equally mixed together? And does every part of our universe look homogeneous and isotropic like our theories expect it to? So these are some of the big universe questions that the Roman Space Telescope is going to help us answer. We'll also be able to study exoplanets with both the main imaging instrument as well as with the coronagraph. By looking at stars in the night sky, we can actually detect exoplanets through a unique method called microlensing. This is not how we commonly look for exoplanets, but it is one way that we can find them if we have frequent observations of stars in the night sky. Microlensing is shown on the left-hand side here. The idea is that you have an observatory down here where the graph is, and you are staring at two stars in the night sky. You have some distant star back here, just a normal star, no planets necessarily orbiting around it. And then you have a star with an exoplanet orbiting around it that happens to cross in front of that distant star. Now, in this case, we are not looking for light being blocked or anything like that. What we are actually looking for is the influence of the foreground star with an exoplanet lensing or bending the light from the background star, causing it to look brighter and to also look potentially a little bit distorted by our telescope. So if you imagine a star passing in front of a distant star, what do we see? Well, we see the brightness of the distant star get brighter and fainter. The gravitational influence of the foreground star actually causes the background star to look a little bit brighter. That has to do with Einstein's physics and the bending of space-time and all of that. We don't have time to get into those details today, but that is the reason for that. And if this star has an exoplanet, when we see the light bend around and get brighter from the distant star, we will also see an additional blip from the microlensing caused by the exoplanet orbiting the star as well. So this is a more complicated and tricky way of discovering exoplanets, but the Roman telescope is uniquely capable of looking for exoplanets in this way. We'll also again be able to directly image the exoplanets if the conditions are right. If we can block out the starlight and potentially see planets physically orbiting around their stars. The graph on the right shows the types of exoplanets that Roman is going to allow us to see. Here you have distance from the star and then planet mass and Earth masses. And so far, we have been able to find a lot of moderately sized planets, so Earth and Jupiter sized planets, that orbit very close to their star. Roman will allow us to see planets of a variety of masses that tend to exist further away from their stars. This is a unique thing that we can see with the direct images using the coronagraph. We're able to see big planets that orbit a bit farther away from their stars than many of the exoplanets we've discovered so far. So Roman is going to look for exoplanets in some unique ways and kind of probe an area, a region of exoplanet science that we haven't been able to really study until this type of telescope. All right, so that is the basics of the Roman Space Telescope. It is actively under construction along with the cameras, the coronagraph, and all the other associated instruments. And if things continue to go well, this telescope will launch 2025-2026 timeframe. So I'm really excited for this one, and I definitely can't wait to see some of the amazing pictures that come back of the night sky. Let's switch gears now and talk about the Rubin Observatory. We'll start by talking about Vera Rubin herself. Vera Rubin did her undergraduate work in astronomy at Vassar College. Here you can see a picture of her using a device to look at photographic plates and study stars up close. She got her PhD in astronomy from Georgetown University in 1954. And she actually applied to and wanted to go to Princeton, but she was barred from going to Princeton because at that time, they did not allow women to do graduate work in astronomy. I think it was something like 25 years after she applied. That was the first time that Princeton allowed women to be graduate students in astronomy. So instead of going to Princeton, she went to Georgetown, did some fantastic work there. After getting her PhD, she worked as a professor at Georgetown for a few years and then became a researcher at the Carnegie Institute of Science. She was also a really strong advocate for women in astronomy specifically. She, as we mentioned with Princeton, battled a lot of people saying, you know, you can't do this because you're a woman. And Vera Rubin constantly said, forget that. I can do anything. I'm just as good as all of my male counterparts. Specifically, one of the funny things that I remember hearing that she did is she took a lot of observations at the Palomar Observatory. And that observatory, until she went there, really had never had women as astronomers staying there for long periods of time. And there was no female restroom. There was just restrooms for men there because that's the only people that were there. So she had to make her own restroom, and the way she did it is she cut out a little piece of paper, she kind of shaped it into a skirt, and she taped it right over the little picture of the man on the bathroom door and made herself a women's restroom at the observatory. So she was very spunky like that, and really took all of this in stride and just said, you know what, I can do anything I set my mind to. And she definitely did. She definitely did some amazing work in the field of astronomy. So Rubin did a lot of great work, but she's most well known for her work with galaxy rotation curves. Here we have a picture of the Andromeda galaxy, and overlaid on top of this are measurements that Vera Rubin took of the rotation rate of stars around the center of the galaxy. So you basically have here distance from the galactic center, and then this is how quickly the stars are orbiting. Now, based on Kepler's laws, which govern gravity and tell us how the planets orbit around our sun and things like that, we expected that when a rotation curve was made, that the stars closer to the center of the galaxy would orbit faster, and the stars farther away from the center of the galaxy would orbit slower. This is exactly how planets orbit around our sun, and based on our current understanding of gravity, we expected that this would translate to stars orbiting around black holes and galaxies as well. If you look at the data here, that's not at all what Vera Rubin found. She saw that near the black hole, the stars orbited pretty quickly. Then their rotation rate dropped off a little bit. So the further away you got from the black hole, their rotation rate went down a little bit as expected. But then not too far away from the center, the rotation rate of the stars goes back up and continues to be roughly constant all the way out to the edge of the galaxy and beyond. These stars are essentially orbiting around the galaxy too fast, much faster than we anticipated based on our understanding of gravity. What does this mean and how can this happen? Well, this is actually direct evidence for dark matter, this mysterious matter that we can't see that appears to be concentrated towards the edge of the galaxy. If there is additional mass, additional matter at the edges of galaxies, that can influence the rotation rate of stars and cause them to orbit faster than we originally expected. This is what we saw, or this is what Vera Rubin saw in M31 in the Andromeda galaxy. And this appears to be true for our own Milky Way and for many other galaxies that have rotation curves that have been made since Vera Rubin's work. So she was really the first person to find some direct evidence that dark matter existed at the edge of galaxies, and that's what she's most known for. So how did the work of Vera Rubin and others lead to the idea of the Rubin telescope and observatory? Well, it all started with this concept of large all-sky surveys. Since the early 1900s and even before then a little bit, astronomers have been photographing the night sky, trying to get a general census of where everything is. Where are all of the stars and galaxies? How are they distributed and how do they change in time? On the right-hand side, we have an example photograph from an early survey from the 1950s. This is a picture of a photographic plate from the Palomar Observatory, one of the places that Vera Rubin worked at, or I should say took some of her data at. This is a picture of primarily stars within our galaxy taken by the 1.2 meter telescope. And to get a survey of the entire night sky, all of the locations that the Palomar Observatory was able to view, it took about 7 years to do this entire sky survey. That's a long time, but we now have pictures of every spot in the sky that the Palomar Observatory is able to see. As time moved forward, we built bigger and better telescopes that were able to take more pictures of the night sky in a slightly more frequent manner. And here is one example of a modern survey. This is a picture of a portion of the Sloan Digital Sky Survey. This data was taken starting in 2000, and the Sloan Digital Sky Survey is still an active observatory today. It's a 2.5 meter telescope located in New Mexico, and it is constantly scanning the sky, taking more pictures, and giving us a general census of all the stars and galaxies that it is able to see from that location. What you see in the picture here is primarily what the night sky looks like and the distribution of galaxies in both space and time. So as we look further and further out, so that's away in space as well as earlier in time, you can see all of this green and red dots here, and that's representing the location and distribution of galaxies in the universe. The galaxies seem to be roughly equally distributed, kind of making a filamentary structure. So there's a few, pockets of galaxies and galaxy clusters here and there, but overall, galaxies are generally equally distributed throughout this portion of the universe. Surveys like this, done with digital cameras, allow us to get better images of the night sky and probe deeper beyond just looking at the stars in our galaxy, but seeing galaxies beyond our own. And now looking forward, astronomers want to build, bigger and better telescopes that are able to survey even deeper into the night sky, and also look at the night sky more frequently. It took years to do both of these surveys, both Sloan and the Palomar survey. With the Rubin telescope, we are going to be able to conduct surveys on a much faster time scale. And that means that we will be able to probe the night sky for potential changes on timescales as short as a few days. So let's take a look at that in a little more detail. The concept that ultimately led to the Rubin Observatory was originally called the Dark Matter Telescope. And it's exactly what we just described, basically a large telescope, an 8.4 meter telescope, that would be able to conduct a deep sky survey that would help us better understand the distribution of dark matter within galaxies and galaxy clusters. So here on the right-hand side, we again have a picture showing a galaxy cluster. So all of those yellow dots are not stars, they are actually galaxies clustered together in space. And you see these blue arcs in the picture as well. These are actually galaxies behind the yellow galaxy cluster, whose light is traveling towards us in space. The light gets bent around the galaxy cluster and both magnified and stretched out. That's why it looks kind of like a wispy curve around the cluster. Above the picture here is kind of a cartoon showing what's happening. The blue swirls that you see here, that's actually this galaxy here. Earth is in the bottom right. And as the light from that distant galaxy passes through the galaxy cluster, that's the yellow galaxies in the front, that light is bent and distorted by the mass and the dark matter contained within these galaxies. And based on these curves, the distortion of the distant galaxies, astronomers are actually able to map the location and the amount of dark matter contained within these galaxy clusters. So this 8.4 meter dark matter telescope was designed primarily to do this, right? To look at gravitational lensing and to map dark matter in galaxies. This telescope was originally renamed to the Large Synoptic Survey Telescope, or really this telescope idea gave birth to the Large Synoptic Survey Telescope, with one of the main goals of doing this type of dark matter survey. It's this LSST, or Large Synoptic Survey Telescope, that was ultimately renamed the Vera Rubin Observatory. So this 8.4 meter telescope is actively being built in Chile in South America. And it primarily observes at visible wavelengths, though it does have a little bit of UV and infrared capabilities because we can get a little bit of that light here on the ground on Earth. And to accomplish some of the goals that we've talked about in surveying the night sky and searching for dark matter, this observatory is going to have the largest digital camera in the world, 3,200 megapixels. And we'll talk more about that in just a moment. It's also going to have a really large field of view, 3.6 degrees. That's huge. The full moon is about half a degree. So you can think of lining 7 full moons up in the sky, and that's the diameter of the field of view of this telescope. So it's just a really large patch of sky that we are able to observe at very high quality, very high resolution all at once. Since this telescope is located in Chile in the southern hemisphere, it will be observing primarily the southern night sky. And it's going to observe the entire night sky once every few days for 10 years straight. So this is a little different than the Roman Space Telescope, where scientists get to pick and choose what they want to look at. The Rubin Observatory is purely a survey instrument. So this will just scan the night sky over and over and over again for 10 years straight. So this telescope is going to be able to provide a lot of images and basically do an all-sky survey over of just a few nights' time. So we'll be able to understand how things change within the night sky on very short timescales. Let's take a look at the optical system of this telescope because it's a little bit different than what we normally see inside of telescopes. This is a tertiary system, meaning that there are 3 mirrors that are used. And what's unique about it is that the third mirror is actually carved into a part of the primary mirror. So on the left-hand side, you have kind of a sketch that shows the primary mirror, which is the outside here. The third tertiary mirror, which is carved and has different curvature in the center of the primary mirror. And then there's also a secondary mirror up above that will reflect the light back down to the third mirror. The whole mirror is 8.4 meters wide, and it's not actually cut out like this. It is a full circle. Just the cartoon on the left shows a cutout to show the material that is supporting the mirror underneath. But the basic idea of how the light comes in is shown on the right-hand side. So on the bottom, we've got our mirror. Light comes in from outer space, hits the primary mirror along the edge here. This light is then reflected back up to the secondary mirror, which is a smaller mirror that hovers above the telescope. This is pretty standard for telescopes to have a secondary mirror. The light comes back down again, strikes just the central portion, that tertiary mirror that has a bit of a different curvature. And after striking that mirror, the light goes back up towards the secondary, but is brought to a focus at the instrument system, which hangs down at the center here. So the camera system that's taking the pictures is all kind of right here. This 3-mirror system does a couple of things. It helps shorten the focal length so that we can get that really wide field of view of the night sky, just like the Roman Observatory has. And the third mirror also helps prevent distortions in a large field of view. Whenever you are looking at a large portion of the sky, the edges of the picture often get a little bit distorted just because of how optics work. But having this 3-mirror system helps reduce some of that distortion and give you more crisp, clear images. So this is how the optical system works. And we can take a look at the digital camera. Remember, we said this was the largest digital camera in the world. And I don't just mean in terms of megapixels and data collection, I also mean in physical size. This digital camera is 5.5 feet tall. So here's the camera system, and here's, an outline of a woman standing next to it. And here's an actual photograph kind of underneath, looking at the detector and sensor system within the camera. So it's literally gigantic. It's 189 individual 16 megapixel detectors for a total of roughly 3,200 megapixels for the whole camera. And this camera is so big that it's going to take 20 gigabytes of data every 40 seconds. That is a tremendous amount of data. So just as we saw with the Roman Observatory, the Rubin telescope here is also going to take a tremendous amount of data and information. And IT people and the engineers have had to design new ways of being able to get the data to the astronomers and allow them to access it virtually, because many of our computers cannot handle 20 gigabytes of data all at once for analysis. So this has been a whole other challenge to deal with, not just designing the telescopes and engineering them, but also engineering how are we going to utilize and analyze the data that we get. So this is really spectacular. Now the camera also has a filter wheel associated with it, or I really shouldn't call it a wheel. I guess it does turn as the cartoon shows, but it's a little bit different than your standard filter wheel. Because the camera is so big, there's actually a mechanism, an arm here, that will select the filters out of the filter wheel, lower them down in front of the camera for us to take the pictures, and then when you want to change the filter, it will lift the filter back out and then rotate the wheel and grab the next filter. You can see here, this is the filters being worked on in the lab. They are huge, right? Because the camera is huge in and of itself. And there will be 6 interchangeable filters so that you can get 6 different wavelengths of light for each patch of the night sky. So all of this data and the frequency with which we are taking pictures of the night sky is going to lead to something really cool. Over the 10-year survey, this telescope is going to generate a movie, essentially, of every spot in the night sky it's able to observe. And for most spots in the night sky, we will have about 825 pictures, maybe more for certain regions. So you're basically going to have an 825 frame movie in 6 filter Technicolor of the entire southern night sky. So this means that we'll be able to basically play this movie and see how the night sky changes over this 10-year time frame. Absolutely spectacular idea. So the last bullet point there, I actually snagged a quote from a talk that I listened to about this telescope. And the scientist basically said, once this is all set, we'll have trillions of data points allowing us to study billions of objects in the night sky. So just a tremendous amount of data, as we have already said. So let's finish up by talking about some of the science goals of this observatory. With repeated observations of the night sky on these short timescales, remember we are observing the same patch of sky once every couple of days, astronomers are going to be able to do what we call time domain astronomy. That's basically looking at a variety of different objects and studying how they change in time. We can look at things like variable stars that physically change size and brightness. We can look for supernova explosions and measure the distances to galaxies. We'll be able to find asteroids and measure their orbital parameters, and I'll talk more about that in a moment. And also monitor galaxies, active galactic nuclei. Look for outbursts in brightness of black holes at the centers of distant galaxies. So all sorts of different astronomy can be done here. The picture on the right, if you watch it closely, you can actually see some stars blinking a little bit. This is a little movie of a star cluster called M3. So what you're looking at here, all of these dots are stars in a star cluster within our galaxy. And the ones that you see blinking are what we call RR Lyrae stars. These are variable stars that change brightness over short time frames. We're talking hours to days. And this video was created in a single night. So all of the flashes and brightness changes that you see are happening within, a roughly 8 to 10 hour time frame here. So the Rubin Observatory is going to allow us to study variable stars like this, and specifically objects that change on short time scales. Right? Previously, it took years to get multiple pictures of the night sky, of the same spot in the night sky. Now we'll get these images, once every couple of days, and really be able to study these short time scale changes. Whether they're stars or galaxies, we'll be able to spot them. We'll also be able to, as we said, look for asteroids and also study the history of our own solar system a bit. So by constantly studying the night sky, we'll be able to monitor the orbits of 5 million asteroids in the asteroid belt between Mars and Jupiter. Potentially watch 100,000 near-Earth objects, make sure they don't crash into our planet, and also look towards the outer edges of the solar system, out where Pluto is in the Kuiper Belt, and monitor around 40,000 objects out there as well. Here in the bottom, we have some pictures. This is some images of a Kuiper Belt object. So everything you see in the picture here is either a star or a galaxy, except for the little dot at the end of the red arrow. That is a rock, a Kuiper Belt object, moving against the background objects in the sky. And we'll be able to create movies like this with the data from the Rubin Observatory. We can also, in monitoring the orbital parameters of all of these objects in our solar system, get a sense of how those orbits relate to one another if they do, and potentially detect the presence of a possible planet 9. That is an additional large planet far beyond the edges of Pluto, whose gravity is either currently influencing some Kuiper Belt objects or maybe influenced the positions of their orbits at some time in the past. So there's a group of Caltech astronomers that kind of kickstarted this idea of another planet based on some orbital parameters of Kuiper Belt objects that seem to make a close approach to the sun, all at the same rough location in the sky. So Rubin will be able to study this in a little bit more detail and maybe actually figure out if Planet 9 truly exists or not. Finally, the Rubin Observatory will be able to do what the Dark Matter Telescope was hopefully going to do, study dark matter. So we'll be able to look for that gravitational lensing like we discussed to determine the location and concentration of dark matter in galaxy clusters. And we'll also be able to look at dark matter within our own Milky Way galaxy by studying how dwarf galaxies orbit around our own. Here we have a cartoon of the Milky Way, and these are what we call tidal streams. Basically, small galaxies that have orbited around and passed through the Milky Way throughout our history, leaving behind gas and dust and stars. And we can actually see them in the night sky. Here on the bottom is actual observations of collections of stars within these tidal streams. And by studying the location and distribution of these tidal streams, we can get a sense of how the Milky Way's dark matter has interacted with these galaxies, and how any dark matter within the dwarf galaxies has interacted with the Milky Way. So moral of the story, we'll be able to study dark matter both near and far with the Rubin telescope. The current status of this observatory is that it is actively under construction and almost complete. You can see some drone footage of the building here on the right. There's a crane here that was lifting in some of the telescope equipment through the slit in the dome. And then here's an interior view of what the telescope looks like. First light is expected in fall of 2021, with full surveys to begin in 2022. So the Rubin Observatory will be completed and online before the Roman Space Telescope gets launched. But both of these telescopes are going to be producing some great science in just the next couple of years. All right, so I just want to conclude by saying that the Roman and Rubin telescopes are really going to work together to provide some amazing science for us in the near future. We are going to get an incredible amount of public data that can be used to make discoveries in a ton of different areas of astronomy. And we will soon have really large surveys of data covering the entire night sky at high resolution and high time frequency, which is something we've never been able to do before. And my personal hope is that these telescopes will help inspire more women to become astronomers. So be on the lookout for news stories and new data and discoveries from both the Roman and Rubin space and ground-based telescopes over the next couple of years.